So welcome back everyone to this talk on primitive stable and Bowditch representations. So here I wrote a few reminders of the first part of the talk. So on the one hand, we have Bowditch representations, for which we have that the translation length grows linearly with the word length, but this growth is only on primitive element in the group. So this is the main difference, for example, with convex or compact representations. And on the other hand, we have primitive stable representations, which say that whenever you take a primitive element and you look at the primitive geodesic that it generates in the Cayley graph, it is sent via the orbit map to a CD quasi-isometric embedding. So what is important, I recall, is that the constant CUD are uniform in gamma. So the main difference between these two definitions is that in the second one, for primitive stability, we have information on every subword of a primitive element. Whereas in the first definition, in Bowditch representation, we only have information on primitive element. And of course, when you take a primitive element and you take a subword of a primitive element, in general, you have no chance that it is primitive. So this is why this is the main difference. So now I would like to talk about the equivalence. Okay, so it's not hard to check that primitive stable representation are in particular Bowditch representation. So you can look at the definitions and convince yourself. So Minsky already noticed that when he defined primitive stable representation. But to have the converse, we have to wait a little. And this is a theorem by Lee and Su, 20, and independently by series. So this is a theorem in PSL2 of C. And so primitive stable representation of F2 in PSL2 of C is the same as Bowditch representations. Okay, but so since we define Bowditch and primitive stable representation in general delta hyperbolic space, we can ask if this result still holds in delta hyperbolic spaces. And so the answer is yes. Okay. And so for X delta hyperbolic geodesic and proper, we have the same equivalence. So this enlarges the previous result. And for example, for iso of X, you can take any rank 1 Lie group. So for example, the isometry group of Hn or the isometry group of any complex hyperbolic space, etc. Okay, so before saying a few words on the proof, I want to give like a geometric interpretation of F2. So F2, it can be seen as the fundamental group of the once punctured torus. Okay, so I will denote the once punctured torus by T star. So in F2, we defined the primitive elements, and they are in bijective correspondence with simple closed curves on the torus. So by simple, we mean that there is no self-intersection and that it is non-peripheral. And the last analogy I want to draw is that in this case, the outer automorphism group of F2 is in fact the same as the mapping class group of the torus. So this invites us to define. So we can define Bowditch representation and primitive stable representation for surface group, possibly with boundary. So you just replace the word primitive by a simple closed curve. And you replace the action of the outer automorphism group of gamma by the mapping class group of the surface. So question, do we have the equivalence in this context? So as far as I know, the answer is not known in general, but so we have still an answer in the case of F2. This gives an answer for S is equal to the once punctured torus. And we can also give a positive answer when the surface S is the 4 punctured sphere. We take the sphere and remove 4 points. So in this case, we can also prove by similar methods that the set of Bowditch representation for this surface is the same as the set of primitive stable representation. So as a corollary, what do we obtain? We obtain that the set of Bowditch representation of F2 and the set of Bowditch representation of the fundamental group of the 4 punctured sphere, we obtain that they are open domains of discontinuity. So for the action of the outer automorphism of F2 and respectively the mapping class group of S04. So, okay, so now I'd like to give some ideas of the proof. But before getting right into the proof, I would like to talk a bit about primitivity in F2. So the main point is that primitive elements in F2 are in bijective correspondence with rational slopes. So it is Q and you add also infinity. So where does this come from? We can see it by taking the map from F2 to Z2. So this is the abelianization map. And remark that it is constant on conjugacy class and that it sends primitive elements of F2 to primitive elements in Z2. So in fact, it gives a map from the set of primitive elements in F2, so up to conjugacy and inversion. So and in fact, when we talk about a primitive element, we mean a conjugacy class of primitive elements. And so this map goes to the set of primitive elements in Z2 up to plus minus. So this is exactly Q union infinity. Okay, so this map, in fact, is a bijection. And this is what we will call the slope of a primitive element. So this means that whenever we have a primitive element, we can associate to it its slope, which is a rational number. And recall that every rational number, we can decompose it into its continued fraction expansion. So this is n1 plus 1 over n2 plus 1 over etc. until 1 over nr. So r is what we call the depth of the continued fraction expansion of the ration. And so we will use this continued fraction expansion. Okay, so now starting from a slope, P over Q that we decompose into N1, etc. until NR, how to construct gamma. So in order to do that, so I will give an algorithm that will do that for us. So suppose that we have this number N1, N2, etc. until NR. And now we will construct recursively, so the words W0, W prime 0, Wi at step I, W prime I. So at level I is equal to 0, we fix A and AB. And then Wi will be Wi minus 1 to the power Ni minus 1 and W prime I minus 1. And the other one will be the same, and you change the exponent to Ni. Okay. So what does this construction? So proposition. So when we do this procedure recursively, at every step, so for every I between 0 and R, Wi and W prime I is a basis of F2. So in particular, Wi is a primitive element, and so is W prime I. So we can consider a slope, and so the slope of Wi is exactly N1, N2, etc. until Ni. So you'd stop at I. And the slope of W prime I is the same, but you add +1 for the last integer. And so how do we get gamma? So gamma is essentially WR. So in fact, gamma is a cyclic permutation of WR. So this gives us a method to construct a primitive element starting from its slope. Now I want to define Li of gamma to be the length, so the word length of Wi. Recall that Wi depends on the integer N1, etc., so it depends on gamma. So this is a number that depends on gamma, and we have as many numbers as we have integer in the continued fraction expansion of gamma. And this length will be particularly important, as we will see it in the following lemma. So lemma, which we can call magic length lemma, is so the following one. If you take a primitive element and you take an integer I between 0 and R, so it means that you look at a certain level of the decomposition of gamma. And now you take U to be a subword of gamma of length Li of gamma. So you take any subword but of a particular length. Then, so after possibly changing its last letter, U is a cyclic permutation of Wi of gamma. So it depends on gamma. Okay. So in particular, they say that up to a small change, the subwords of this specific length are simple. So this is structure results on the structure of primitive elements. And so I want us to keep that in mind for what I will say later. Okay, so now we would like to prove that Bowditch representation are in particular primitive stable representation. So take one and for all a Bowditch representation. And what do we want to show? We would like to show the following proposition, which will be the main step, the most important part of the proof. We want to find a constant k such that for every primitive element in F2, such that for all these elements, if we look at the orbit map on the primitive geodesic generated by gamma, it is included in the k neighborhood of the axis of rho of gamma. Okay, so maybe we'll draw a picture. So whenever we have a primitive element, it is sent to an hyperbolic isometry. So hyperbolic isometry has an axis. So here is the axis of rho of gamma. And so we look at the orbit map. So the orbit map travels in the space like that. This is the orbit map. But what we want is that the orbit map stays in a bounded neighborhood of the axis. So this is K. So in fact, what we want to prove is we want to prove the Morse lemma for this particular geodesic. So how are we going to prove that? So let us try to understand what happens if this is not true. What if this is not true? So I'm doing proof by contradiction. So this means that we will be able to find an element gamma that will be big. We have to think of it as a big element gamma. So we have the axis of gamma. But for this element, the orbit map will go far away from its axis. Okay, so this is the orbit map. But when we have this configuration, this means that we can find a point here and another point here, such that the 2 points are at the same distance, k, of the axis, and such that in between, all the points on the orbit map in between stays at a distance at least k. So during this part of the orbit map, we follow a subword of gamma, and let's call it U. And so this configuration, we will call it a k excursion. U is a k excursion. So this is a definition. Now let's give another definition and take a positive number, epsilon, and U, an element of F2, not necessarily primitive. And so we say that U is an epsilon quasi-loop if, so the following holds, the distance of rho of U O to O, so the displacement of the base point, is bounded by epsilon times the length of U. This is what we call a quasi-loop. What does this mean? This means that somewhere there is our base point, O, then we follow the subworld U. We go somewhere, but then we have to be back here close to the base point. This is rho U of O. So this is a quasi-loop. So why was I talking about quasi-loop? That because we can prove lemma. So I will write it by hand, that big excursion are quasi-loop. So this is the main idea. So the idea is that I will draw some pictures. Here we have an excursion. Okay, but this is not the right picture. The right picture should be the following one. So you can go far from the geodesic, so from the axis, but then you come back close to this point. So these 2 points have to be close from each other. Okay, this is a picture for this lemma. So how do we use that? So what did we say? We said that we can find a big primitive element, gamma, okay, in which, okay, we will find a subworld U, which is an K excursion. So somewhere here, I found U, and U is a K excursion. But since K excursion, so big excursion, are quasi-loop, in fact, this subworld is a quasi-loop. But now, the subworld U, so it is included in some bigger subworld here of length, one of the magic lengths we have defined before. And one of the consequences of the lemma we wrote is that if we find a subworld of this particular length, we find it at many other places in the word gamma. So for example, here, here, and also here, and also here, etc. So in fact, we have not found only one quasi-loop, we found it at many other places. Here, 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 and here. We can see U in there, U in there, U in there, etc. Okay. So this means that we find a lower bounded proportion of gamma consisting of quasi-loop. But what is a quasi-loop? A quasi-loop is a subworld which displays not much the base point. So in fact, we find a lower bounded proportion of gamma that does not displace the base point much. And then with some more work, we find an arbitrary big proportion of gamma, which does not the base point much. And this will be a contradiction because we have the Bowditch inequality, which is the following one. And so what does this inequality say is that this is large because we have chosen a very large element gamma, and this is small because of because it consists a lot of quasi-loop. So it does not displace the point much. This means that this quantity is small. So this will be our contradiction. And so this will be how we will prove that Bowditch representations are in fact primitive stable representation. So I will stop here and thank you very much for watching this part of the talk and see you later. Bye.